So we will go into this lesson where we talk about what happens when castings solidify and shrink, okay, and what defects are created because of those shrinkages. So first we will talk about why they volumetrically contract, how much they contract, and which part of volumetric contraction leads to defects. Some portion does not lead to defects, and we introduce the concept of what is called as feeding distance and feed paths, and finally a little bit concept of how do you predict where you are going to get the defects, a little bit of that. First thing, let us look at simple physics again. If we look at the three metals, iron, aluminum, iron and copper, the liquidus density value is known, solidus density value is known, percentage density change is 12-13%. Now density is increasing from liquid to solid, which means volume is reducing correspondingly because mass is constant. Mass is density into volume. It is increasing by 12% means volume is reducing by 12%. 12% reduction in volume is not a small amount, it is a big amount. Okay. But where does it really change? If you see the volumetric contraction, and this is a typical graph if you plot for major metals, on the top side you have the temperature, on the bottom you have the volume. So initially it is reducing between pouring and liquidus temperature. When that is happening, the entire casting is completely liquid, please remember that. The next contraction is happening between liquidus and solidus temperature. When that is happening, the casting is in a mixture of liquid and solid. The third contraction is happening between solidus and room temperature. When the casting is entirely solid, it is solid contraction. It is like you heat a metal scale, it increases, you cool it down, it reduces in length. That kind of contraction is the last part of contraction. Okay. Now each one has a different trick to take care of. The first one you do not have to do anything, you just pour excess metal, the level of liquid level falls and that compensates for that, no problem. So that takes care of maybe 2-3% of contraction. The bottom side where the entire casting is contracting in a solid state, that is also easy to take care because you make the mold little larger, when it contracts it comes to right size, you can take care of that. The middle part, which is significant contraction, if you see volumetric contraction, the largest contribution, almost half of total contribution. If total contraction is 12%, almost half of it, let us say 5-6% happens in the middle liquidus solidus, and that is cannot be taken care either by pouring excess metal or by making the mold larger. You have to provide a feeder. Okay. And that is a tricky part of castings. How do you design the feeders properly? Now there are some exceptions to the rule. If you have some metals like grey iron, okay, and to some extent high carbon ductile irons, in between the contraction somewhere there is an expansion also. So if you see the graph is turning to right side, that is your graphitization expansion. Because of that, the total volumetric requirement or feeding requirement does come down, but it does not become 0. So you do need to apply feeders, but you also have to worry that the feeding does not place in the wrong direction, because as graphite is expanding, the pressure from inside the metal pushing the metal out from the casting towards the feeder. So you need to control the feeder neck size carefully, and we will look at that again in the feeder design part of the course. Okay. Now let us understand this very carefully, and I want all of you to wake up if you are partially sleeping. Okay. What you see in this picture is the mold around the casting. It is a step casting kind of a thing, and where you are seeing the temperature contours or solidification contours of solidification from outside to inside. The first layer to freeze is a brown layer, it solidifies first, then your orange layer solidifies, then your yellow layer is solidifying, and finally the white region is solidifying. That is clear? It is layer by layer from outside to inside. Now when any particular layer is solidifying, let us say yellow is solidifying at this point of time, which means that outside brown is already solid and white is completely liquid, yellow is now undergoing liquid plus solid contraction. What happens? 6% volumetric contraction is happening, so vacuum is created there, so it is going to pull metal to fill the vacuum from somewhere. From where? Outside impossible because it is already solid, or it will pull it from inside, which is the white area. So metal flows from the white inner hot area to yellow area, and from yellow to brown and dark brown area. Okay. that is the path along which the microscopic flow of feed metal is happening through dendrites to compensate for volumetric contraction during solidification. And these red lines, which are perpendicular to the isothermal contour lines, are called as feed paths. So feed paths are perpendicular to the temperature contours. Okay. And what happens to the white region? When the white region is solidifying, everything else around is already solidified, and the white region has either directly or indirectly fed the rest of the casting. That ends up with a hole when that is freezing, right? White has fed yellow, and yellow has fed the orange region, orange has fed the brown region. So white region is directly, indirectly has filled up or compensated for the volumetric contraction of the rest of the casting. So whatever 6% of rejection or defect which comes, the hole will sit in the hottest area of the casting, which is in this case is the white area here. That is how shrinkage cavity forms. Okay, clear? The question is it important for us? Okay, what does it really represent for us? So let us take our standard cube casting, which is easy to calculate, 10 centimeter cube. Let us assume a very low volumetric contraction. I am not talking about 6%. Let us talk about ductile iron. Let us say it is 3% volumetric contraction. So what is the contraction value? Cube volume is 100 centimeter cube. 3% contraction gives you how much? 30. Now if you say 30 becomes a spherical hole, what is the diameter of the hole? Can you calculate and tell me what is the diameter of the hole? You can do a rough calculation. You can assume it is a cubic hole instead of a spherical hole. That is easy to calculate. So you are talking about 30 cube root over. Surprise, surprise, it is 3 centimeters. In a 10 centimeter cube, you are talking about a hole size of 3 centimeters with a 3% volumetric contraction. Imagine what will happen if it is 6% volumetric contraction. Of course, in a real casting, you do not see a big hole like that, because you do not get to see all the shrinkage in one place. Part of the shrinkage will go as sink, part will go in some other place as porosity. So that the 6% or 3% does distribute little bit. This is in a short freezing range alloy. If it is a long freezing range alloy, it will distribute even more. Much more portion of the casting is porous. Okay, but remember, end of the day, the 30 centimeter cube in this particular casting has to be fed somewhere. Otherwise, that much of holes or hole area is there in the casting, and that is a pretty big hole. Let us understand that. Okay. Now the hole shape will vary. If it is a short freezing range alloy, you get a concentrated shrinkage cavity. If it is a long freezing range alloy, you get a distributed shrinkage porosity, but distributed around the central hotspot area only. You get little bigger porosities in the hotspot area, surrounded by little more smaller porosities and smaller porosities and all that. So you have larger area which is porous in a long freezing range alloy. Now it can also take different forms. So you saw the first picture already, right? A single shrinkage, concentrated shrinkage cavity is the first example. Little distributed porosity, small holes around a region hotspot, that is called as shrinkage porosity. Okay. You can have one more form which is like central line porosity. If you have a long thick section, you can have a big hole in the center of the thick section. That is called a central line porosity. You can also have a corner shrinkage, and you can see the fifth example as sink. All these are different manifestations of the same phenomenon, which is volumetric contraction of the molten metal. It can take different forms depending on combination of geometry and the material. Now one more important concept, because this will tell us what really we should do to get castings right. It is the beginning of that understanding. So if I take a step casting, okay, and let us say I cut and the whole casting is freezing, and I cut a cross section in section A and section B, the temperature there represents the cooling sequence of cooling. So if you look at say A, the outer one blue cools first, then the central red area cools little later. If you cut the cross section B, you will find the blue area is there, red area is there, there is one yellow area also, which means that both the blues are cooling at the same time. But when in A red is cooling, here red is also cooling, but the inside is still liquid, more liquid is available here. and we extend the argument further, if we go to C, there is much more bigger hot area available in the center section. What I am saying here, in any cross section you see temperatures increasing from the outside to inside, or freezing taking place from outside to inside, like onion shells, and this progress of solidification from outside to inside is called as progressive solidification. Okay. So between from 1 to 2 to 3, location 1 to 2 to 3 in a cross section from outside to inside is called as progressive. Now the interesting part is the other one, between A and B and C, which freezes first? A freezes first, then B is freezing, then C is freezing, and this direction or sequence of solidification from A to B to C is called as directional solidification. Do we have to worry about it? Yes and no. In a casting, depending on the shape and material, it will anyway solidify in particular manner, but a foundry man has a lot of tricks up his sleeve to control this. At the end of the day, your goal is to control this direction solidification in such a manner that you get defects in a place where it is okay to have the defects, which is a feeder, and you do not get defects in a place where you do not want defects, which is a critical section. So there are a lot of tricks to control the direction of solidification in casting, and we'll see those controls tomorrow. But right now what we are understanding is we want to achieve controlled progressive direction solidification. That is the goal of a good feeding system. Now here is a funny sequence here. So let us say I have 3 sections of different thicknesses. Just a question of how I organize them. The first picture is what we saw just now, is ideal solidification. Your thin section is freezing first, then you have a thicker section which is feeding the thin section, and then you have an even more thick section next to the middle section which is feeding that. The entire defect is shifted to the left side in a hot spot, which is easy to feed. You can put a bigger feeder on the left side and you can take care of this casting, no problem. The second one is a minor problem. Okay, middle part of casting is freezing first. On both sides you have 2 hot spots. One is a big hot spot, one is a small hot spot. Big hot spot you can take care of by a big feeder. Small hot spot, either you put a smaller feeder or you put some other tricks like a chill, but then you have to take care of both sides. Okay, it's not one side only. So it's a minor problem, but it's a solvable problem. But the last one is really bad, and many uncastable castings are because of this inaccessible hot spot. This hot spot, where do you put a feeder? Put a top feeder, not possible, side feeder, not possible, and you cannot access that. And that creates a major problem because that place will have a defect. No matter what you do, you will have at least a minor shrinkage porosity there. So it always worry about configurations of hotspots and accessible and inaccessible hotspots. Of course, there are some tricks to make them accessible, which we will see again in the last part of the course. Now feeding, we understand, we have typically what's called a feeding distance. So we say the feeder is effective for a distance of about 2 times the wall thickness. If plate thickness is T, a feeder is effective for a distance of 2 times the thickness from the feeder end, from the end of the diameter of the feeder. But more important, and I want you to again pay attention on this slide, I want to now discuss how do you want to create shrinkage, because in a laboratory conditions we always have to create shrinkage. Many times we fail in that. You want to create good castings and you also fail in that. So if you understand how we succeed, okay, we can show you how you can succeed also. So we have succeeded in understanding how to create shrinkage in a laboratory conditions and how to control the parameters. So I will share that knowledge with you. Most of it is known from literature, so it's not that I am not inventing the wheel here, but I am at least explaining to you in a nice way here. So let us take this step casting, and let us say I have put thermocouples in the casting at fixed distances, and the temperature red line which you are showing is a plotting temperature. Initially all the points at a higher temperature at time tau 1, after some time temperature falls. If you notice, temperature is falling more at the end and falling less at the thick section, which is acting like a feeder. Okay. What I also want to notice is the gradient. You remember the temperature gradient definition, dt by dx. In this case, if you know calculus, dt by dx is nothing but the slope of this curve. Where is the slope maximum? At the end. Okay, at the end slope is very high. It's also reasonably high at the feeder end. Where the slope is really very low, in the middle part of the casting it is almost flat, dt by dx is flat, there is no gradient there. So now I give you my conditions. If you really want to create shrinkage cavity, if you want to create a shrinkage cavity, please remember that, okay. You want to create a defective casting, keep the temperature high at some place. You have a hot spot, create a hot spot in a casting, you will get a shrinkage defect there. Okay. In this case, hot spot is at A, at the feeder end or the thick section, middle of that you have a high temperature. Definitely guaranteed you will get a hot spot shrinkage there. Condition 2, keep the gradient low. If you see at A, the gradient is not very high, it actually becomes flat. And also another area, we see middle part, the B area, temperature is fairly high and gradient is really low. Conditions are favorable for again what is called as center line shrinkage. Okay. And one more condition in the reducing order of importance is the cooling rate. If my cooling rate is high, I am saying it promotes shrinkage defect. Is that clear to you? Or do you think it's something wrong in the slide? You think cooling rate should be low or high? If cooling rate is high, what happens?
The thinner portion will get solidified faster. No,
okay.
it should be low.
Yeah, that's what. So there is a confusion here. Okay, so let me explain that properly. And you have to grasp this logic properly here. First, let me put a disclaimer saying that the condition 1 is the most important condition. If there is a hot spot in the casting, you don't have to even look at condition 2 and 3. Please remember that point first. If temperature is not so high, it is somewhat high, like in the section B, I start looking at condition 2 also, which is gradient. And unfortunately here, gradient is low, and so condition 1 and 2 are both satisfied, so I get a defect in B area. Now I am looking at B is, let us say temperature is not that high, even more lower, okay, gradient is low, I am not so sure, and I look at third parameter which is cooling rate, and I am checking that if cooling rate is very high, then I get a defect anyway. How I am saying that? The condition is, when I say gradient is low, there is some gradient available, small gradient is available, let us say. So metal is possible to flow from here to there. It is trying to flow, this value is freezing, vacuum is being created, but there is a temperature is not so high, little low, it is trying to flow, but as it is flowing, the cooling rate is high and it freezes off in the middle, it will not reach and it will create a shrinkage cavity. So high cooling rate promotes shrinkage defect. So of course from your point of view you can just reverse the thing and say low temperature, high gradients, low cooling rates are good for not having defects. The reverse of that is for good quality castings. You got the logic for cooling rate, okay? If cooling rate is high, the feed metal is not able to reach. No, we are not talking about, we just said if it is high, then you have problem, and cooling rate can be high for various reasons. It could be geometry there, maybe you put a chill there, maybe section is too thin there, all those conditions. So those conditions leading to fast cooling rate in an area where it is flowing through is bad for the area which is trying to be fed. That's all. And how to control that, as I said, we will talk about tomorrow. But I will show you beautiful slides where we see the cumulative effect of different conditions in a mode for these cooling rates. Okay, so you really want to predict where shrinkage, porosity or cavity will happen. There is a nice way to do that. Let me explain that in a quick thing here. What we say is, what we learned from previous slides is that if temperature is high and gradients are low, you have a problem. But how high and how low, you put some cut-off limits. So you say that if temperature is greater than, let us say T max, okay, or some 0.9 times T max, and it is lower than, let us say 0.9 times, let us say G max, okay, you can, or in the band, you can see the band there. In the macro band, in this band if temperature is there, in this band gradient is there, you say it creates a macro shrinkage. Similarly, if the temperature are in the micro band, gradients are in the micro band, you say it creates a micro shrinkage. But again I said you cannot do hand calculation of temperature gradients, you have to do it through simulation. But simulation also you can now start looking at automatic interpretation of results. So program should tell you where you will get a defect and things like that. but that is how these programs work. The other way these programs work is by looking at the critical solid fraction, at what place the proportion of solid to liquid in the metal is now exceeding, let us say 2/3, 0.6 times. There you say start getting a defect. That is one way of looking at it. The other two they say is, if the temperature gradient is below 200 degrees per meter, you start getting a problem, central line shrinkage. The third criteria they talk about is a Niyama criterion, where they talk about gradient and cooling rate. We mentioned that high gradient, low cooling rate is good or bad? Is good quality castings. Low gradient, high cooling rate is bad for getting defect. So Niyama criterion says that if it is less than 1, you start getting a problem there. Now here is a real example of a real casting. So if you see this, there is a shrinkage porosity in the cut section, okay, and there is a clear hot spot in the cross section where you see there. The yellow area is a hot spot there, and that's an example of. And if you see the gradients, temperature gradients, they are all accumulating in the hot spot area and stopping there only. So all the gradients are converging in the hot spot area and stopping there only. Ideally, your gradient should converge into the riser, which is not happening there. Okay, so what you learned today is one is during conversion from liquid to solidus, there is a significant amount of volumetric contraction, almost half of the total volumetric contraction of a casting, which itself is very high, about 12-13% for many metals. So most contraction for most metals are in the range of 3 to 6%, which represents a huge amount of gap to be filled up. That filling up happens from inside the casting itself, from thinner sections to thicker sections to thicker sections. And ideally what we say is, if you can control that where it is solidifying last, and if you can somehow control that and push it out into the feeder, then we get a good quality casting. Now the distance to which a feeding takes place from a thick section, thin section depends on your geometry, which drive your temperature gradients. Okay, and we also said you get a shrinkage defect at high temperature, low gradient, or a good quality casting at wherever you have low temperatures and high gradients, which is like end sections. End sections have low temperatures and high gradients there. Okay.